Our next example starts a kind of class of examples that we're going to use a lot. And this example is due to the mathematician Dirichlet. And it's really kind of a weird function, at least for the sorts of functions that we're generally used to. It's kind of unusual, right? So the way that this function is defined is f is going to be 0 whenever we plug in a rational number, right? So f of a half is 0, f of 0 is 0, f of 2 trillion is 0, f of 6 over 34 is 0, right? Any fraction gives us 0. But if we plug in any irrational number, then we get 1. So f of pi would be 1, f of square root of 2 would be 1, f of square root of 3 over 17 would be 1, and so on. All right, now this is a perfectly legitimate function because it assigns exactly one value to every input, right? This is a rule that assigns a unique value to every input. And I do still want to encourage you to graph this, even though it's physically impossible. But there's a way to kind of graph it that is suggestive of what the function does, and I think will be key to a lot of the examples that we do. So I want you to sort of get in the habit of graphing these kinds of things. So let me just do it here. So I've got 0 and 1. Now, I mean, this really is an impossible task because, remember, the rationals are dense in the reals, and so right between any two rational numbers, there's a real number. Between any two real numbers, there's a rational number. Same for irrationals. And so you basically have like an infinitely discontinuous function, and the way we graph it is we sort of indicate that by what we'll call a fuzzy line. So we'll, right, whenever we have an irrational number, we jump up to this fuzzy line, and if we have a rational number, we're down here on this fuzzy line. Right, so even though this is not exactly the graph, this is indicative of what the graph looks like. Right, so we jump up to 1 whenever we have an irrational number. We stay at 0 when we have a rational number, and we're indicating that this happens right so often that we just get this sort of fuzzy cloud of points, or this fuzzy line of points at 1. All right, now our one tool so far to show that a limit doesn't exist is the divergence criterion, which requires us to produce two sequences whose limits under f are different. Now our sort of rule of thumb when we have a piecewise function like we do here is sort of cleverly select a sequence that stays on the top part and then a different sequence that stays on the bottom part, and that gives us a good shot of getting two different limits under f. Right, now we're interested in the limit as x goes to 0, so our sequences have to approach 0. So I'm going to let x be a sequence of rational numbers that approaches 0. And one of the easiest one of those is 1 over n. So xn is rational and approaches 0. And I'm going to take yn to be an irrational sequence that approaches 0. You can arrange this a number of ways. I think we've proven that square root of 2 is irrational. And we did a homework problem that showed that therefore square root of 2 over n, and it was a more general result, but square root of 2 over n has to also be irrational. So we have y sub n is irrational, but also tends to 0. All right, now let's look at the action of f on each of these sequences. So f of xn is f of 1 over n, but because all of my xn's are rational numbers, right, the function is 0 there. So that goes to 0. It's a constant. And f of yn is f of root 2 over n. All of those are irrationals, and so they all evaluate to 1, and so the limit is also 1. All right, so we've done what we needed to. Two different sequences, both converge to 0, but the limit of each sequence under f turns out to be different. So since xn goes to 0 and y sub n goes to 0, but the limit of f of x sub n goes to 0, which isn't 1, which is the limit of the y sub n's, by the divergence criterion, the limit itself doesn't exist. It's a y sub n, not a 1 over n. Okay, so it's a sort of bizarre looking function, and we're going to use this to create other bizarre looking examples. But this is kind of a model for how you would show a limit of one of those doesn't exist. You can look at the graph and kind of see that no matter how close we get to 0, right, we'll have some points at 0 and some jump up at 1, and there's no way we can avoid that. Right? And then what we see sort of graphically and intuitively is confirmed by a suitable choice for the two sequences that give two different limits under f. So the divergence criterion guarantees that we don't have a limit there.